So my name is Jeremy Wells. I'm a local civil engineer. I grew up in Monte Vista and live in Alamosa now. And I'm here to talk about Strawbale construction in the building code. So I just got a building permit this week, woohoo, to build a Strawbale house in Alamosa County. And so in the research that I've done as a civil engineer, kind of get the way building codes work and all that, wanted to take that research that I've done and share it with you about how to build a Strawbale house according to the code. So I'm actually going to get some handouts that I should have had ready, but just give me 2 seconds. So the reason that I chose a Strawbale house myself is I've always wanted to build a house and just turned 40 this year. So I've had plenty of time to think about it and looked at every type of house there is. And just like Steven said down at the demonstration site, if you're going to build a house yourself and put a lot of the sweat equity in it, there's nothing better that I've found than a Strawbale house, because it's very friendly to somebody that doesn't have a whole lot of construction experience, goes up really fast. It's the building materials are really inexpensive, and it's just really easy to figure out. And the people that have gone before us have figured it out already. They've gone through some of the best ways to do it, and just like you saw Paul and Steven down there, they've figured out the most efficient ways to do it, and they've also figured out what the strength of the wall is through a bunch of testing. So the title of this is Strawbale Provisions in the IRC. IRC stands for International Residential Code. So it's kind of like a cookbook for how to build a house, like 1 family to 2 family dwellings. And so jurisdictions all over the country, they adopt this code, and a lot of it's usually the counties that have the building authority, and they usually just adopt the national code, and sometimes they make some changes. But the beautiful thing about the code is, if you build a house according to the code, just like if you use a recipe, you know you're going to get the cake right, or whatever you're baking or whatever. The IRC is kind of like a cookbook for building, and it's typically for conventional building techniques. But it does have provisions for if you want to build something that's not particularly in the code. And that's the way that Strawbale buildings have been built in the past. So in the 1980s and 90s, when Strawbale construction got popular again, what a lot of builders were having to do is the code says if there's a building that you want to do that doesn't have enough evidence that it meets code, the building official has the authority to require testing. And so some of the builders in the 80s and 90s, especially like in Arizona, California, they were building these test walls and actually loading them, testing them, just to prove to the building officials that it was going to work, it wasn't going to fall over and all that. And a lot of that research eventually got into the building code. So I'll just show you a copy of this International Residential Code. It's not like a light reading that you'd want to do at bedtime. But way back at the back of this book, there's a small appendix that says Strawbale construction. It's Appendix S, and that's what I'm going to be talking from. The presentation, this handout, did you get one? Okay, good. The handout goes through just one by one each section of the appendix, and there's only 8 sections, so it won't be too much. Probably be about 45 minutes, and then we'll have plenty of time for questions at the end. So who knew that Strawbale construction was already in the building code, in the IRC? All right, we got a couple. All right, cool. So have you read it yet? Okay. All right, good. Well, that's what I'm here for. So I've read it, and I have got a approval to build one now, so I'm excited. So just a little bit of a history. 2015 is the first year that it made it into the IRC. IRC comes out about every 3 years with a new version. So it was Appendix S, and then in 2021 it was Appendix AS. This book right here is the 2018 version. So this is what Alamosa County, where I live, is going by. They're still in 2018. If you're looking at the most recent version of the IRC, it's they changed it to Appendix BJ. They ended up with so many appendices that they ran out of letters in the alphabet. So in 2021 is the first year that it switched to BJ, but in the newest one, 2024, is still, no, sorry, I got that wrong. 2021 they switched it to AS, so all the section numbers still matched up because they called it section AS whatever. But then in 2024, sorry, it was switched to BJ. Sure. So there's the very first section. I'll just call it section 1. I'm just using the last digit. Just talks about the two different wall systems that are in the code. So there's basically just a load-bearing Strawbale wall and an infill Strawbale wall. So if you're building a timber frame and you're just putting the straw bales in the middle for insulation, those are the two main types of walls. And there's a little more strict requirements if you're using it as a load bearing. So there's section 2 is just a whole bunch of definitions. I'm not going to go through every definition, but I'll just I'll mention some of the main pieces. Here's my model straw bale. So I think almost all of you were at the demonstration site, so you've seen a real straw bale, but this kind of gives you a better visual of how they're done. So the ties go the long way around the bale, and the straw is oriented this way with the bales tying it that way. What Paul didn't like about those bales that we used down there is the straw was sticking up this way. I don't know how that happened, but whatever baling machine they were using, a lot of the straw was vertical this way, and so the ties weren't really holding it together very well. So a lot of this straw was just peeling off. So before you just decide to buy bales, go and look at them and kind of get a feel for, whether you want to build with it or not. This is like a 1/3 scale model. The typical dimensions are like 3 feet long, 1.5 feet this way, and about 14 inches tall. Those bales we used down there were more like 16 inches tall, so they were kind of a little extra fat. You can build with it what's called lay flat or on edge, and it kind of depends on what all you're doing, which way you want to go with. So if you put it up on end like this, you're going to get more wall height for the amount of bales that you use. So you're not going to end up with quite as many bales that you have to buy and stack. And actually the insulation value is about the same, whether it's this way or this way, because it's so much more dense in this direction. You're actually going to get pretty close to the same R value. So one reason that people don't like building this way is because of these ties. If you want to like notch around different beams or posts that you have in your construction, you can notch a little bit of that out this way. But if you try to notch any of this bale out this way, you're going to cut the strings, the ties. So that's one of the major determinations. In a little bit, I'm going to talk about how tall you can get the wall, and the wall height that you can build to in the code is based on the width of your bale. It's a ratio of the width to the overall wall height. So you can get, if you lay them flat, you can also build your wall a little bit taller because it's more stable overall. A few other definitions. Clay. I'm sure you all know what clay is, but you might not know what it really is, what makes it clay. So the reason clay acts the way it does is that it is the particles themselves are like microscopically small, and they're not just microscopic pebbles like sand is, but they're actually like flat discs, and so they're able to slide against each other, and that's what makes it able to mold. And so it's different than silt. Silt is just like almost like sand, only smaller. So if you have a bunch of silt in your soil, it's not really going to hold together like clay does. It's going to be more like mud. If you were down there at the demonstration site, the way we were stacking like a full height bale on one side and then moving it to the other side on the next course, that's called a running bond. And that's a much better way to do it than putting all the stacks straight on top of each other, because you get that extra strength from the offsetting the joints. Pre-compression, yeah, feel free to move around, get dry. Pre-compression is like there at the end when we were compressing the straps and tightening the straps. I'll talk a little bit more about that, what the code says about it. And one thing that was not talked about down there is mesh, pins, and a shear wall. So mesh and pins are two different ways that you can add some reinforcement to a straw bale wall. And I'll talk more about where exactly those are required here in a little bit. But mesh is just like you can use a metal or plastic or natural fiber fabric on the outside of the wall, and it's embedded in the plaster. That makes the wall stronger. And then you can also use pins, like you can use metal rebar, you can use bamboo or wooden dowels, and you can put those in the center or on the outside, and those also make the wall stronger. So that was section 2. The last one is a shear wall. So imagine, can you all still hear me? I guess it is a good idea I had a microphone. The rain's a little loud. So, can you hear me better now? Okay. So, if I have forces going right against the wall like this, that's called an out-of-plane force. So anywhere in the code where it says out of plane, this is the plane of the wall. And I'm not talking about a bale anymore. I'm talking about, this is a whole house. So this is the plane of the wall. An in-plane load is like a vertical load right on the top of the wall, or a load like this. And an out-of-plane is like a wind load coming against the wall. Got another little prop here. So if you're looking at a wind load, this is another house. So if you take out these walls and you have wind here, it's not gonna hold that load very well. So having this side of the house or the box, that's called a shear wall, because it takes load from this wall, and the ceiling or the roof structure, it takes this wind load and it spreads it out to this wall and this wall, and those are called shear walls. So that's an important part of the building code, is determining how much shear walls you need to be able to take those loads. I'm not going to be able to read my notes here in another minute or two because my paper's already wet. So the next section, section 3, is all about bales. So the straw bales themselves. We talked about the size of the bales, and you've seen the size of the bales. The building code also talks about the density, the dry density of the bales. And it's actually got a minimum density, dry density of 6.5 pounds per cubic foot. So you can weigh your bale and divide it by the dimensions cubed to get your density. But that's the dry density, so you also have to subtract any moisture from it. And the moisture requirement for a straw bale is less than 20%. So you can get these fancy little tools that measure the moisture of your bale. This one I got off of Amazon for like $80. And it reads the moisture directly in percentage. So if you're, I'd actually, when I was doing the dry run and thinking to myself about this presentation, I was saying to myself, you know, around here it really doesn't matter because it's so dry around here. But, you know, if you've had bales sitting out in this weather, you should definitely check the moisture before you put the plaster on and before you stack other bales on top of a wet bale. Yeah? The reason you're testing for moisture is because you're testing before you put the plaster on. And so once you put the plaster on, the wall is still going to breathe a little bit, but if there's moisture inside that wall when you seal it up with plaster, you could have mildew problems, mold problems. You heard Steve talk about like spontaneous combustion, where you've got the temperature is actually going up because of the decomposing process that's happening in there. You can search on YouTube for this guy that grows sweet potatoes inside of straw bales. So, like, there's enough just natural moisture in a straw bale that you can grow sweet potatoes inside of it. Yeah, it's really interesting. So straw will decompose if it's exposed to oxygen and moisture. So you want to check the moisture level, make sure that you're not going to be enclosing a wet bale that's going to decompose inside your walls. So the straw types, there is a difference between straw and hay. Some people talk about building hay bale houses, and that's not something you want to do. Hay is for horses, as the old saying goes. So straw is actually the stems from like wheat or barley or oats, where you harvest the seed heads, and the stems is what they turn into bales. So the baling machines were invented like in the late 1800s, and it wasn't long after that they started using them for building out in Nebraska. So section 4 is all about plaster. In the building code, well, first I want to talk about like what the plaster's for. The straw itself is not what provides the wall its strength, actually. It can provide some strength, but what's really happening is you're making something like kind of like a beam. So if you think of an I-beam or even a sheet of cardboard, the two pieces on the outside is where all the strength comes from. This piece called the flange or called the web on an I-beam, that's really just to connect the two flanges together. So all the strength is out here, and the middle is just to connect them together. And same with cardboard, the two sheets of paper on the outside are connected just by a squiggly piece of paper. That's what makes cardboard strong. And it's the same way with a straw bale wall. The plaster on both sides of the bale is really what gives all your strength. So they've done testing on just straw bales themselves and how strong they are before you put the plaster on them. They can hold a whole bunch of weight before they fail, but they also like just keep compressing and compressing and compressing like a spring. You don't want your 8-foot ceilings to become like 5-foot ceilings, so the load is all transferred to the plaster itself. So you want to make sure you do a good job on plaster. There are 4 types of plaster in the code. there's a clay plaster, which you can use, like if you have enough clay in your soil, you can use your own soil from the ground to do your plaster. And there's 2 different tests to determine if you do have enough clay in the building code. These are really simple tests. You don't have to have any equipment or anything. One test is just to make these little balls, so 3/4 of an inch diameter, and you let it dry out of the sun, and if you can just break this between your thumb and your fingers, like that's the actual test in the code, you shouldn't be able to break it. So you want to try to break that? Here you go. Here you go. You can just toss it on the ground. It's not littering, it's just dirt. It's clay. It's dirt with clay in it. So did anybody break it? Okay, that's good. Because my soil, that came from my ground, and I actually didn't pass this test. So that's the first test. That tells you how strong it is. And then this is the second test, is called the ribbon test. And you should, you make this string of soil about the size of your finger, and you should be able to hang it from your hand and it doesn't fall apart. So I can get about like 3 or 4 inches, but once I try to have like 6 inches out, it fails. So you should be able to hang the length of your hand, it says. It doesn't say whether it's length of your hand this way or this way. But it basically just tells you if you have enough clay to bind the sand together. So mine, I probably don't have quite enough clay in that mixture. This is a jar test, and this is not a test that's actually in the code, but if you're just curious about, like, if you don't pass one of these tests and you're curious about how much more clay you're going to need to bring in or mix with it or whatever, you just fill the jar about halfway with soil and the rest of the way with water, shake it up, and just let it settle. And so the sand, the heaviest particles will settle out first, and then you'll get a layer of silt. So that's the layer where you can just barely see the specks. And then the last layer that settles out is the clay, and it just looks like a solid color. You can't see the individual particles. So this mixture, I've got about maybe 10 or 15% clay. You want to pass that around? So it's a typical plaster. It doesn't tell you in the code exactly how much clay you need to have, because every soil is a little different. It just gives you these 2 tests, the kind of the flexibility test and the strength test. But a typical clay plaster will have about like 20 to 30% clay. So I'm a little short on the clay in that mix. You can really use anything that you can get that's a clay. The best thing to do is just look around for anybody that's got free dirt that was like that they didn't want because it wasn't structural enough. Like if you're building a driveway or something, you don't want clay. So if somebody's dug out some dirt from their land, thank you, sir. And they advertise free fill dirt, just go make some plaster and see if it works. Yeah, I'm only familiar with bentonite and like well drilling and that sort of thing, because I know it has a really high capacity for expansion. So if you have too much bentonite in particular, you're probably going to get a lot of cracks because you're going to put your plaster on your walls and then it's going to shrink and you're going to get a bunch of cracking. So maybe anything except bentonite.
No, that's why I was asking. I was just curious if there was something specific.
Yeah. Yeah. Yeah, I'm not really familiar with all the different terminology of clay that a geologist would use, but yeah, another really good idea is um, to do some test walls. Like we did a test shed out on our property where we put some plaster up on the wall and we were able to see how much it shrinks and how workable it is and all that. So the other types that I'm not going to talk about as much because just using your own dirt is really fun. But there are other types of plasters you can use. So you can use a soil cement where if you don't have enough clay, you can add a little bit of cement to your own soil to give it a little extra strength. You don't want to add too much. It's about a 10 to 20%. At least 10, but no more than 20% is what the code says of cement. So if you have just coarse sand on your land, you don't want to use that because if you mix sand and cement together, you get concrete or mortar, and it's not going to be breathable enough for a straw bale wall. It's actually just using straight cement is not allowed in the building code because it's not breathable enough. You actually want the plaster to be able to kind of soak that any moisture that is in the bales and transpire it out into the air. So you're not allowed to use just cement. You can use soil mixed with cement. You can use lime, and you can use a lime cement mixture. So there's whole books written about plasters. The code doesn't really go into it a whole bunch other than to give required strengths of the plasters and what I already mentioned about if you're using clay plaster. So the thickness, you're typically about an inch to an inch and a half is the thickness of a plaster. If you're using a soil cement or lime plaster, it can be 7/8 of an inch. And I have no idea how you could get your plaster thickness down to within an eighth of an inch of what it's supposed to be. So I just say 1 inch. You're actually not allowed to have any more thickness than 2 inches. Again, because you want some permeability to get moisture out of the wall if it ever is in there. I think the last thing I wanted to say is you're not allowed to use stucco or straight cement plaster as a finish over a clay plaster. This has been done a lot, like down in Taos and different areas where they're restoring old adobe buildings. They put like a cement stucco over the top of this adobe structure, and it just like flakes off and cracks because there's no way for that moisture to get out. The adobe also kind of expands a little bit, and the cement just can't handle that flexibility. It's too strong and rigid.
Well, and they're also finding that with the lime on the clay plaster too, because they absorb moisture at different levels, and so these houses that were built 20-25 years ago that people put lime on top of clay, they're now finding delamination.
Okay. Yeah, it actually is a requirement of the code to put a lime wash, it says, on over it. Yeah, so if you are required to put a lime plaster finish coat or a lime wash, like a kind of like a thick lime pasty paint mixture. You're required to put that anywhere where the clay plaster is exposed to rain. So with the wind you get in the San Luis Valley, that's pretty much any exterior wall because rain can go straight sideways, So, but you're right. You don't want to have too thick of a lime plaster on top of a clay plaster.
Well, what a lot of plasters are doing now is adding lime to that base coat,
Mm-hmm.
the scratch coat of the clay plaster. They're putting lime plaster on it, and then that helps to adhere the lime to the clay because the clay has been rendered with lime.
Okay, yeah, that makes a lot of sense, and the code gives you more strength permissions for if you have a lime plaster, because the lime does add some strength definitely to the clay.
Mr. Chairman,
Yeah.
does the IRC define exactly how thick or what layer or how many layers of this lime wash or extra?
It just says a finish. So you can, if you're making like a lime wash, There's only so thick you can get it without it just running down the wall.
Would you say like 2 coats feels good on the outside of all that?
Yeah, it only requires a single coat, and it just really provides like a seal for erosion protection. Because clay, if you haven't fired it like pottery, it turns back into mud if it gets wet. So like the adobe buildings down in Taos, you can see like at the base of the walls where rain has dripped and splashed onto the base of the walls. There's some places where they've made repairs that are like 8 inches thick, where they just let it erode over a decade before they finally repaired it. So yeah, the lime wash, it just requires a single coat, and it's just to give it some weather resistance, and it makes the maintenance much lower. So if you don't have that protective weather protection over the top of it, you're going to be going out there as a tradition every spring and redoing your plaster like they do at the Taos Pueblo that's been around for like 1,000 years. Yeah.
With the work you've done, do you have like a footer or a splash wall on your structure?
I'm going to have my structure about a foot above the grade. So, just seeing the buildings at the Taos Pueblo, it was a little less than a foot that was being eroded. But the building code says 8 inches between the bale and the ground, and it says 6 inches between the plaster and the ground. So you have the sill plates that I'll talk about in a little bit that kind of get the bales up another couple inches above your foundation. So you can have 6 inches to the plaster, 8 inches up to the bales is the code. And one thing that Paul mentioned is if you've got a high snow load, it's probably a good idea to make that higher, however much you're thinking that the snow is going to be drifted against your wall would be a good idea. So trying to read my wet rag here. So yeah, typically 1 inch to 1.5 inches thickness. The code says that a clay plaster should be applied in at least 2 coats. But if you're doing like 1.5 inch or 2 inch thick walls, I would really recommend using more than just 2 coats. So typically you do 3 coats. And if you're like 1/2 inch each coat, you're probably not going to get too much cracking at that point. But that's what you run into with a clay plaster is when it dries, it's going to be cracking a little bit from the shrinkage when it loses that water content. The next section, section 5, is all about walls. So it talks about just walls that are just standing as infill, and then it gives extra requirements for structural walls. But the wall heights, if you just have a strawbale and clay wall that is not reinforced with anything, you can have the height of the wall be 5 times the thickness of the bale. So if your bale is 1.5 feet wide, then 1.5 times 5, that's how high you can have it. So it's only about like 6 bales, 6 courses high, which is about a 7.5 foot high wall. So if you want to get your wall any higher than that, then you've got to use some type of reinforcement. And if you do use reinforcement either with pins or mesh, then you can get it up to like 8 times the thickness of the bale. So then you're up to like 12 feet high. So you're going to be plenty high enough for any kind of typical residential ceiling height if you use some pins or some mesh. The pins, a lot of people in the past used pins for reinforcement, and they used like threaded rod or rebar right through the center of the bales. And the problem with that is if you've got to put your bale down over a metal rod, then once you get it down over the rod, it's fixed where it's at. You can't like push it real tight into the next bale. So you've got a little spot for less insulation value in the overall wall. So the straps that were down at the demonstration site, those don't provide the reinforcement that's described in the code to get a higher wall height. Those just compress the bales. The straps are to compress the bales so that the bales don't settle after you've got some load on it. But if you've got a wall like the wall that we built down there at the demonstration site, once you get up to a certain height, it's kind of like Jenga blocks or something. It's doesn't have a whole lot of support, and you can have. I had a whole bunch of boxes that I could stack, but it's kind of hard to hold a microphone and build at the same time. But if you've got, I'll just do it with two. It'll be a really short wall. If you've got a bunch of wind load and these bales are not tied together, then you get at the top of the wall, you're going to get some deflection, and the bales are not acting all as one. And so even if you've got a strap, the strap isn't rigid, so the strap can have some slack on this side, and that gives it the opportunity to stretch out on the other side. And so your clay plaster that's providing all the strength of your wall, it can't hold itself together in tension. So once you have a wall that's going like this, you're getting major cracks in there. And so what the pins do is they tie this whole wall together before you put the plaster on, so the wall has to all move together. And you can do the pins internally, which is not a good idea, or you can do them externally. So you could put a dowel on both sides, and then you tie them together through the wall. So you can do that, tie them together across the top of the bale course before you put the next course on. You have to do it every 32 inches, so you can put 2 courses on before you have to do another tie. And those pins have to be every 2 feet along the wall, whether they're internal or external pins. Sill plates, you're required to have a sill plate under each outside face according to the code. So the sill plate that we put at the demonstration wall actually does not meet building code because we used a single sill plate that wasn't as wide as the bale. So what's usually used, and the minimum required by code, is 2 2x4s. So you got a 2x4 over here, and you got a 2x4 over here, and the outsides of those sill plates are flush with the wall. That gives you a place to, it keeps the bale up off the foundation so you don't get moisture from the foundation up into it, but it also gives you a place to anchor those sill plates down to the foundation, and then staple, if you have a mesh reinforcement, you staple the mesh into that sill plate. There's a requirement for how big your pins have to be. I missed that. So 1/2 inch steel or bamboo, or if you're using wood dowels, it's got to be 3/4 of an inch. And there's also a requirement for a water resistant barrier. Before you put those sill plates down, you got to have like a vapor barrier on top of the concrete. If you're putting it right on top of a concrete foundation, vapor barrier, and then your sill plates, and then the straw bales. So the next slide in the handout is a couple of details, whether you're building on a wood floor or straight onto the concrete foundation. So those pictures are straight out of the code. Can't tell if I'm skipping a page with these wet pages. Yeah, I think the next one is so section 6. So that's everything it says about walls. The biggest significant thing in that section is the wall heights and how tall you're able to do those walls. The next section, section 6, is where it talks about structural walls. So if you've got load-bearing walls, the section 5 applies whether you're using straw bales as infill in between a timber wall or using as load-bearing. But section 6 is just for structural walls that are load-bearing. Since the plaster is what carries the load, you have to have the a way for the loads, any loads from the roof, if you're using straw bale walls as a load-bearing wall, you have to have a way for the loads from the roof to go straight into the plaster skins, and then from there straight into the foundation. So the plaster itself has to be supported. You got to have the roof supported on the clay plaster, and then you got to have the clay plaster supported directly on the foundation. So like the demonstration wall, the bales are sticking out wider than the foundation. You can't do that according to code. You got to have a lot of people just put a lip in the concrete. If you got a concrete foundation, a lip for the clay plaster to be on. And those details are kind of shown in those drawings. So you might have heard Paul and Stephen talking about a box beam. We just had a 2x on top of those bales for the compression straps to go around, just because that's how much space they had. But the code says you got to have a box beam. So you've got you've got the 2x's on the sides, like a 2x on each side with plywood top and bottom. And then you got to fill that with insulation, usually just fiberglass bad insulation. But that beam just spreads out the load evenly across the wall so that you don't have like a weak spot in your straw bale or your plaster that ends up with too much concentrated load. Talked about pre-compression. If you're using straw bale walls as load-bearing walls, it does define the amount of pre-compression you need, and you've got to have 100 pounds per foot of wall is the pre-compression that you got to have before you put the plaster on. And I asked Paul how much tension that his crimping or his tightening tool can put on the straps, and he said about 700 pounds. So he had one of those about every foot on that wall. So he was giving 700 pounds per foot of pre-compression on those walls. So it only requires 100 pounds. So you don't have to have too fancy of a tool or be too strong for that. Braced wall panels, I talked about that, the definition of it. It's like these sidewalls that the load gets transferred to keep it from doing that. I'm going to talk in a little bit about the specific requirements of where to put those braced panel walls and how much you need. The next slide lists the strengths, the minimum strengths that are in the code for plasters. So clay, like these little balls that I passed around, clay is required to have a strength of at least 100 psi. This is about just about a half of a square inch. So it should take more than 50 pounds to break this, for it to meet building code. So I'm not sure how much pressure I can actually put with my thumb, but it's probably not quite 50 pounds. The building code says that a building official can require you to get a test done on your plaster. Like if you're using clay plaster, you're not mixing cement into it, and they're kind of skeptical about it. They can make you do a test with like a 2-inch cube, and there's plenty of labs, like geotechnical labs, that could do something like that for you if you ran into that. But they just add a little bit of load at a time until it breaks, and that's how they figure out the strength of it. So you can see soil cement and cement lime, they're 10 times as strong as just clay. So just a little bit of cement makes a big difference. Also makes a difference in the amount of money you're going to spend, though. So the next page gives you the allowable load-bearing, the allowable loads you can put on a load-bearing wall. So with just a clay plaster with no mesh reinforcement, you can have up to 400 pounds per foot on your wall. So once you get to like a 20-foot wide building with a roof load, you're getting pretty close to that. So it's not a real big load, but it is enough if you've got like if your floor joists or your roof doesn't have to span all the way from outer wall to outer wall, and you've got a middle wall that can take some of that load, then you can get it'll hold enough to have a second floor with a second floor load and your roof load, as long as you don't have too big of a span that's all transferring to those outer walls. And then if you have a soil cement or cement lime, you can get twice that much, like 800 pounds per linear foot of wall is what it'll carry. The next slide, so slide 13 in the handout, I called it allowable vertical loads, but that's wrong. That's the braced wall panel types. So the way that the code talks about braced wall panels, like these side walls that are going to help keep the building from going like this, those braced wall panels, you have to have a larger length of braced wall panel if your wall's not quite as rigid or strong. So it separates it has a table that separates what type of wall you have, and it's based on what kind of plaster you have and whether or not you're putting a mesh in that wall. And then it's got another table at the bottom, or on slide 15, it's got another table of exactly how long of a braced wall panel you need. So just as an example, if you look at slide 13 and you look at a type A2, which is just a clay plaster wall with some mesh in it. The braced wall panel table doesn't even have an A1 listed in it. A1 is a clay plaster and no mesh reinforcement. You cannot use a clay plaster wall with no reinforcement as a braced panel wall. So according to the code, if you don't have mesh in any part of this wall, then it can't count to be able to transfer these loads into that braced wall panel. So you have to have mesh. You don't have to have mesh in the entire wall, but you have to have at least enough length of mesh to meet the next table on slide 15. So if I look at slide 15 and I look at 115 miles per hour wind speed in that first column, that's the wind speed that they use in Alamosa County. The next column over, if I look at 30 feet, that's about how far my walls are apart on my house. If I look at 30 feet, that's how far these two walls are apart. So if like this is where my braced wall panel is going to be, if they're 30 feet apart this way, so this load on this wall has 30 feet between this wall and this wall, that it's got to spread those two, then that determines how much braced wall panel you need in here. It's how far apart these two walls are. So if they're 30 feet apart, and I look at the next column that says A2 for my wall type, it says 11.2. So that's how much I got to have of these two walls. I've got to have 11.2 of feet of that has to have mesh in it. So that's probably the most complicated part of the code, is those braced wall panels.
Question for you, Mr. Chair.
Yeah.
Does it have to be mesh, or can it be those pins for bracing?
The pins are only for the wall height, to gain wall height for the the thickness to wall height ratio. And those pins can be required even if you're not using it as a load-bearing wall or a shear wall. The pins don't count for anything when you're talking about shear walls or braced wall panels. Good question. The slide 14 is from a different part of the code that just kind of gives some guidelines about braced wall panels. So your braced wall panels are basically at the corners of your, you typically put them at the corners of your structure. You can't have more than 20 feet of between two braced wall panels. And a braced wall panel is basically just a solid piece of wall without any openings. So you can't count a part of a wall with a window in it. You can't count that as a braced wall panel. It's just a solid piece of wall. You put them close to the corners, and you can't have them more than like that 11.2 feet that we looked up. You can't have that more than 20 feet of a gap between the like two different sections that count for that 11.2 feet. And if I'm talking gibberish, just let me know. I can clarify.
So I'm confused. So what determines if a wall is A2,